Dear Chairman, dear colleagues and guests, I am Zlotin Zlatev and I will present to your attention the work Representation of Textile Drapes of Squared Samples from Digital Images with co-authors Liana Indre and Julieta Ilieva. Simulation analysis of textile fabrics is actively used in the design of textile and clothing. The disadvantage of this type of analysis is that the product cannot be simulated with sufficient accuracy. This is because not all factors that affect the behavior of textile fabrics can be known. The ability of fabrics to form rounded, beautiful details and fit well to the body is known as draping ability. It depends on the flexibility of textile materials and their thickness. The Q6Dix method makes it possible to simultaneously determine the draping ability in the different directions. This method uses a round shape of the sample, but there are variants with the rectangular shape of the sample. An advantage of the method with rectangular drapes is that the directions of the weft and the warp can be easily distinguished. Also, the larger the drapery area, the greater the variety of shapes obtained. Simulation analysis of rectangular draperies requires knowledge of the characteristics of textile fabrics that affect their formation. For this reason, the recognition and analysis of rectangular fabric draperies would be more effective if digital images of real samples were used. As the method with rectangular draperies is not standardized, it is necessary to look for more criteria for assessing the change in the drapery of textile fabrics. It is also necessary to do research on the relationship of the features describing the drapery with the well-known and more commonly used methods, such as Q6 drape measurement method. Samples of textile waste textile products have been prepared. They are 30 by 30 centimeters in size. They contain textile fibers of cotton, polyester and elastan. The diagram of laboratory setup with its general view and principal schematic is presented. Position 1 shows the sample of the textile fabric after draping. It is placed on a cylinder with position 2. In the cylinder, there is a lightning fixture with position 3, which is a diode lamp. A video camera with position 4 was used for obtaining drape images. The distance from the video camera to the sample is 32 centimeters. Color digital images of draperies were taken with a resolution 800 by 600 pixels. The drape coefficient DC is obtained by methodology of Spahio et al. Using standard drape tester. Also, fabric's mass and thickness were determined. Indices that describe the geometry of the drapes are presented with their mathematical formulas. They are calculated by short and long axes of the draperies. An algorithm for calculating the characteristics of drapes and visualization of their three-dimensional shape has been used. Stage 1 load the original RGB image. Stage 2 conversion to HSV and separation of the S component. Stage 3 define the contours of the central disk and the drapery from the image. Visualization of the number of pixels per millimeter was used. Stage 4 calculation of the coefficient of the drapery according to the mathematical formulas presented above. And stage 5 calculation and visualization of the three-dimensional shape of the drapery. An example of the algorithm work is presented by video record. the general view of this paper is presented. Also, drape as a picture. After the execution of the algorithm, "3D drape" is obtained. The selection of informative features for predicting the drape coefficient DC was made by the relief method. To predict the drape coefficient based on reduced data from the geometric characteristics of the draperies, the methods of principal component regression (PCR) and the partial least squares regression (POSR) were used. To determine the quality of the obtained models were used coefficient of determination R squared, sum of squared errors SSE, and root mean square error RMSE. The table shows data on the textile fabric samples used. They are represented by their minimum and maximum values, as well as by mean and standard deviation. After the selection of informative features were selected that have weight coefficients above 0.6, determined by relief method, the number of features is halved. The presented vector of 7 features was obtained. The results of the prediction of the draping coefficient DC, the vector of features is reduced to 2 principal components and 2 latent variables. They describe the variance of the data over 95%. As a result of PCR, a coefficient of determination R squared equal to 0.83 was obtained. The errors are SSE equal to 9.33 and RMSE equal to 2.34. This shows that after reducing the vector of geometric features with 2 principal components, drape coefficient can be predicted with 83% accuracy. As a result of POSR, a coefficient of determination R squared is equal to 0.89. The errors are SSE equal to 6.39 and RMSE equal to 1.94. This shows that after reducing the vector of geometric features with 2 latent variables, drape coefficient can be predicted with 89% accuracy. Examples of 3-dimensional shape of draperies. A deviation of 3 to 5 millimeters from the actual dimensions of the draperies was found. Obtaining data through the proposed algorithms and procedures is up to 8 seconds. Validation of the obtained models has been done. Accuracy over 65% have been achieved. In comparison with Zhu et al., the techniques proposed in the present paper for analysis and visualization of draperies from quadrangular specimens have the advantage of using simplified procedures that do not require the processing of the outer contour of the drapery to be done with complex computational procedures. The studies of Han et al. Have been supplemented by proposed algorithm, which does not require data on the mechanical properties of textile fabrics. It is necessary to make more analysis for the effective use of the tools proposed in this paper. For example, Petrak et al. Indicate that the application of standard test methods such as ASTM D1777 and ASTM D3776 would lead to a more efficient simulation of the behavior of textile fabrics and also to improve the economic effect of the study. As a conclusion, an algorithm for creating a three-dimensional shape from two-dimensional images of draperies prepared with square samples is proposed. With this method, the shooting conditions are known in advance, as well as the basic dimensions of the objects in the image. Automated software tools have been adapted and then tested to use the proposed methods and procedures for analyzing digital images of draperies, which will be used to describe the shape and predict the characteristics as well to classify them into groups. Analytical models have been developed for automated prediction of the draping coefficient, which can be used to predict changes in the property of textile fabrics. The advantage of the proposed tools is that simplified procedures are used, which do not require the processing of the outer contour of the drapery to be done with complex calculation procedures. The study can be continued by performing additional analysis of the outer contour of the draperies. The results presented in this paper can be used in the design of textile products such as curtains, tablecloths, napkins, blankets, clothing and fashion accessories. Thank you for your attention.